The question is, will you need to know this intuitively? No, that's something that I would have to give to you. I mean, it's actually true that a lot of things, the correct answer is something symmetric. In this last problem, the minimum turned out to be exactly halfway in between because there were sort of equal demands from the two sides. And similarly here, what happens is if you elongate one side, you get less. It actually is involved with a two-variable problem, namely if you have a rectangle and you have a certain amount of length associated with it, what's the optimal thing you can do with that? But I won't, in other words, the optimal rectangle, the least perimeter rectangle turns out to be a square. That's the little sub-problem that leads you to this square bottom. So that would have been a separate max-min problem, which I'm skipping because I want to do this slightly more interesting one. All right? Okay, so now, here's our formula for A, and now I want to follow the same procedure as before. Namely, we'll look for the critical point, or points. So let's take a look. So again, A is x squared plus 4v over x, and A prime is 2x minus 4v over x squared. So if we set that equal to 0, we get 2x equals 2v over x squared. So 2x cubed, well, how did that happen to change into 2? Interesting. Guess that's wrong. Okay. Right, so this is x cubed is equal to 2v, all right? And so x is equal to 2 to the 1/3, v to the 1/3. All right, so this is the critical point. So we are not done, right? We're not done because we don't even know whether this is going to give us the worst box or the best box from this point of view, the one that uses the most surface area or the least. So let's check the ends right away to see what's happening.